So let's do an example with a prism as an example of refraction. So the way a prism works, have a triangular piece of glass, and then light comes in, it bends at one surface, bends at the other surface. And so what I want to do is figure out the angle of deflection. So let's assume that we've got an isosceles prism. Okay, the apex angle here is 32 degrees, and light comes in parallel to the base. Okay, so when it hits that surface, it's going to refract, hits that surface, it's going to refract again. And so I want to know what angle is this final exit relative to the parallel to the base. Okay, so first step is we need to figure out theta 1, because that will give us theta 2. Well, it's an isosceles triangle here, and so that means that all the angles add to 180 degrees, but these two angles at the base have to equal each other. So 180 minus 32, and then take the result, divide by 2. That tells you that each of these angles is 74 degrees. So if that's 74 degrees, that's 16 degrees right there, which makes theta 1 16 degrees. Okay, now all we got to do is find theta 2, and what we need to know is index refraction. So let's say the index refraction outside is 1, so it's going to be air. Index refraction of air is just slightly bigger than 1. It's 1.0003. And so, but that's going to be 1, you know, to the number of significant figures that we typically worry about. Index refraction here, let's say it's glass, 1.52. And so Snell's law, call that N1, N2, N1 sine theta 1 equals N2 sine theta 2. Well, if you go through the math there, then theta 2 turns out to be equal to 10.4 degrees. Okay, so now we need theta 3. Well, theta 3 is going to be equal to 90 degrees minus theta 2, because this is a perpendicular right there. So theta 3 turns out to be equal to 79.6 degrees. That allows us to find theta 4. Theta 4 is going to be 180 degrees minus theta 3 minus 32 degrees. So that's going to equal 68.4 degrees. Okay, so now we want theta 5. Theta 5 is going to be 90 degrees minus 68.4 degrees, so that's 21.6 degrees. Okay, now we want theta 6. Well, N2 sine theta 5 equals N1 sine theta 6. So we go through the mathematics there, and theta 6 turns out to be equal to 34 degrees. Okay, well, that gives us theta 6. So with that, we can get theta 7. Theta 7 is going to be 90 degrees minus theta 6. So that would be 56 degrees. So 56 degrees. Okay, but we want to compare that to what this would be. Well, this angle here is going to equal 74 degrees. So theta 8 is how far we are from the perpendicular. So theta 8 is going to be equal to, so theta 8 is going to be equal to 90 minus 56 degrees. So, 74 minus 56 degrees. So that's going to be 18 degrees. So we have an 18-degree angle right there. Okay. Now, that's the example here for this prism. If the prism happens to be in air and with light. Now, thing about light is not always do you have exactly the same index of refraction for all wavelengths. There's a physical principle called dispersion. Now, dispersion says that different wavelengths of light or different frequencies of light have a different index of refraction. And you can think about how this sort of works, that you have different frequencies of light, and so some of them are trying to move things back and forth faster than others. The electric field flips back and forth quicker, so that's going to have a different impact when it passes through matter. And so what you realize is typically for a higher frequency, the index of refraction is normally going to be a little bit higher than for a low index of refraction. So for a higher index of refraction, so let's say that for a different wavelength, a longer wavelength, then let's say the index of refraction for our prism instead is going to be a little bit different. So for our prism, we set index of refraction 1.52. Let's assume that was for a long wavelength. So for a short wavelength, let's let the index of refraction be 1.58. Okay, so a little bit higher. How does that change things? So how does that change? Well, once again, this is 32 degrees. Now this index of refraction is 1.58. It's still going to be the same outside. That's still 74 degrees. That's still going to be 16 degrees. So the difference is now theta 2 is going to be different. So theta 2, once again, we have N1 sine theta 1. Theta 1, once again, 16 degrees, okay, equals into sine theta 2. So theta 2 now turns out to be a little bit different. Before, it was 10.4 degrees. Now it's 10.0 degrees. So theta 3 is going to be exactly 80 degrees. So theta 4 over here is now going to be 68 degrees. Theta 5 is now 22 degrees. Okay, so now theta 6. So again, it's going to be equal to into sine theta 5 equals N1 sine theta 6. So we can solve for theta 6. Theta 6 is now 36.3 degrees. So theta 7, 90 minus 36.3 is 53.7 degrees. Okay, and so this is still 74 degrees. And so this angle, theta 8 is going to be 74 minus 53.7, so that would be 20.3 degrees. Okay, so what does this mean? For a longer wavelength, it bends here, bends here, bends there. But for a shorter wavelength, it bends a little bit more, bends a little bit more. And so we have dispersion right here. So the first one here was, if you remember, that was 18 degrees. And then this one is 20.3 degrees. So the dispersion between long wavelength and short wavelength, so this is going to be long wavelength, and that's going to be short wavelength. So the dispersion here is going to be 2.3 degrees. That's my difference here. Okay. Now, if you remember, for the electromagnetic spectrum, you know, red, orange, yellow, green, blue, indigo, violet. This is the long wavelength then. The longest wavelength you see is about 700 nanometers. The shortest wavelength you see is about 400 nanometers. So what that means is, as white light, which is all the different colors, go through the prism, it's going to spread out here from red, orange, yellow, green, blue, indigo to violet. So that gives you the dispersion, or the range of colors that you would see in the rainbow that is produced by the prism. So this is an example of using a prism and dispersion. So two different concepts here. So we got geometric optics. Now notice how we solved this. We had lots of triangles. We had lots of geometry going on. We used Snell's law twice, but most of the time we were drawing this with geometry. So to solve a problem like this, the best solution is to draw it really big. And if you draw it really big, then you're most likely to be able to get the correct answer, because then you can like show everything and show all your steps and so forth. And then you can actually see what you're doing. It also sometimes is helpful to use colored pencils to solve this and draw each step in a different color so that you keep track of it all. So those are just some operational steps that kind of make solving all these things a little bit easier.